In Chapter 3, we finished the first half of Chapter 3, which was modeling conduction resistance and convection resistances by resistors in a thermal network. We worked 3 problems last time doing just that. So today we kind of transit to the last part of Chapter 3, which is a new topic. It's called extended surfaces, and it talks about how we engineers take heat out of something or maybe even add heat by convection. So we're looking at how convection can help us enhance heat transfer. Back in Chapter 1, Newton's law of cooling, Q equal H A T surface minus T infinity. So let's say that you're in a group, automotive group, and you're in the radiator group, and you have to design a radiator to take the heat out of the engine. So here's your equation. It's Newton's law of cooling. You've got to find a way to make that Q big. Take all the heat out generated by the combustion processes, take that heat out of the engine. So the hot water goes from the engine into the radiator. Okay. Now, look, you can see the equation. There's different terms in there. So you might say, well, okay, I'll look at the parentheses, Ts minus T infinity, surface temperature minus free stream temperature of the fluid. This Ts you can't play with. For instance, somebody's going to tell you the water comes out of the engine block at this temperature. It's got to be at this temperature after it warms up and you've driven 3 miles. So that's coming out of the engine block. Can't play with that, because I could say the bigger I make that, the more heat's going to go out of the engine, out of the radiator. No, you can't play with that. You say, well, wait a minute now. What if I make T infinity really small? If I make T infinity really small and this difference becomes larger. Say, well, maybe I'll put in the owner's manual, only operate this car when the outside temperature is less than 25 degrees C. Huh? I'm not going to buy that car. No, you can't play with that. This car has got to drive in Phoenix in the middle of August, 120 degrees Fahrenheit, and up in Anchorage in the middle of winter. So no, you can't play with that. So you can't play with this. Okay, you say, all right, that didn't work. You know what? That H, right now on the outside of the radiator, the tubes carrying water, hot water, are cooled by air passing over it. And I know water is a better convection media than air. So rather than blow air over the radiator, maybe I'll have like misters blowing water over the radiator, and that'll take more heat out of the radiator. You're right, but who's going to pay the penalty of a 50-gallon water tank in your trunk? You go to the gas station, fill up your gas tank, then fill up your water tank. No, that's not going to work. You're stuck with it. It's called air. You put a fan in front, that helps, thank you. The fan helps, but the fluid you're stuck with is air. Say, okay, that didn't work. Wow, I'm left with that guy. Interesting. The bigger you make A, the bigger Q gets and the more heat you take out of the radiator. I can make the radiator in front of the car 4 feet by 3 feet. No, I can't do that. The car sits down here. You can't play with that. I got to find a way to make the area greater and fit in under the hood. You know what I'm going to do? I'm going to add fins. Yeah, that's the whole point. That's the whole point of the last half of Chapter 3. You're going to add fins, extended surfaces. What do? They take more heat out in an automotive radiator. So we engineers use fins for a ton of things. The guys who do electronics and so on, they tell us, I got to keep this stuff cool, because if it's not kept cool, it's going to fail. So you guys design fin surfaces. Design me a fin surface for whatever I have to take heat out of something. So yeah, we have to do a lot of fin surfaces to take heat out of all kinds of things in this world. And you can also add heat. Baseboard heaters around the perimeter of a room carrying hot water, they're finned behind a little thin metal sheet. And the air from the floor goes there and gets hot from the finned surface and rises into the room. So you can also add heat to like the air in a room by finned surfaces. Well, to find out what's going on with finned surfaces, we start out with this model. And let me erase this. I'll erase the little crosshatch right now. Here is a finned surface. The surface you add the fins to is called the base. So the base is the area that you add fins to. Here's the base, TB. Here's the fin. Its length out from the base is L. Its width is W. Its thickness is T. Its thermal conductivity is K. This particular fin is called a rectangular fin because the side view of the fin, here it is a rectangle. Rectangular fin. That's the first one we'll look at. We'll look at other fins later on, but this is the simplest one to look at first. So, we want to get how the temperature varies with X. Don't forget, the first step is usually in a heat transfer problem involving conduction. Get how the temperature varies with X. How do we do that? We model it by a little differential element, which then gives us, when we're done, a differential equation. Right. Okay. So we take a little differential element out of the fin. So here's my differential element. It's dx in length so there's my little differential element, dx, that's the key. Show it over here. I'm going to write an energy balance on my differential element. Okay. Let's assume the base is hot and the fluid's cold. Let's say it's air to make life easy. So the base is hot, the air is cold. Air temperature T infinity, convection coefficient of the air on the surface is H. So how does heat get out of the fin? It's being conducted in this direction, from hot to cold. Okay, heat comes in the left-hand side, Qx by conduction. Heat goes out the right-hand side by conduction, Qx plus dx. It's just like chapter 1, E dot in minus E dot out is 0. This is for steady state, no generation, constant K. Steady state, no generation, constant K. It's also 1D heat transfer. Okay, so what comes in? Qx from my picture. What goes out? Qx plus dx plus Q convection, minus Q convection. What's Qx plus dx? Expand it. Qx plus ddx, Qx dx. What's Qx? Fourier's law, chapter 1, minus K AC dt dx. What's AC mean? Here, there's AC. It's the area through which heat is conducted. C stands for conduction. Okay, now how about convection? Chapter 1, Newton's law, Q equal HA T minus T infinity. What's the area shown here for convection? It's the perimeter times dx. Perimeter times dx. That's the area, T minus T infinity. Put those three guys in here and simplify. And when you do that, you end up with the following. So put those guys in there. Okay, d squared t dx squared minus hp over KAC t minus t infinity equal 0. Now we do some simplification. First one, we let a new variable theta equal fin temperature minus T infinity. Second one, we let a new constant m equal the square root of HP over KAC. This gives, so if you put this in here now, T minus T infinity is theta. D squared T dx squared becomes D squared theta dx squared minus m squared theta equal 0. Don't forget, when you take d dx of theta, that's d dx T minus T infinity. That's d T dx minus d T infinity dx. The differential of a constant, of course, is 0. So, conclusion, d theta dx equal dt dx. And the second partial of t with respect to x is equal to the second partial of theta with respect to x. That's the game you play. But when you're done, the equation looks a little neater and cleaner. The whole point is to make the governing differential equation look neater and cleaner. And here it is compared to the original one. Now, the solution of this, theta as a function of x, C1 e to the mx plus C2 e to the minus mx. So that's a general solution. Exponentials are in the solution. Okay. Now, we know the story again. That's the governing differential equation. We want the solution of that. We've got to find C1 and C2. There's two constants of integration. We need two boundary conditions, two BCs. So, BC number 1. That's the easy one. At x equals 0, the temperature of the fin's the base temperature. Okay, that's what theta base is, T base minus T infinity. Okay, BC number 2. Okay, now I've got a choice of 4 of these guys. Let's take case A first. Oh, this is, yeah, that's okay. Case A. Then we'll have B. Then we'll have C. Then we'll have D. Case A is convection from the fin tip. I'm going to make that a little bit more spaced out there so I can put some stuff here. Where's the fin tip? The fin tip is x equal L. That's the end of the fin away from the wall. Here's the fin attached to the wall. This is the base. Air blows over it. This is L. This is T. This is W. Picture over there. This is the fin tip. This is the fin base. Okay. Convection from the fin tip. Case B is adiabatic fin tip. case C is given temperature at the fin tip. Like if someone said, okay, the fin tip, let's say, the base is at 200 degrees Fahrenheit, the fin tip's at 105 degrees Fahrenheit. Okay, they gave me the temperature of the fin tip, that's case C. Case D is a special case, is infinite fin. Very, very long. The temperature of the fin tip is going to approach the temperature of the air. Temperature of the fin tip is going to approach the temperature of the air for a very, very long fin. We'll tell you what that, well, we'll tell you what that is in just a minute. I'll put it down now. Only if ml greater than or equal to 2.65. And when I work a problem to show you in class next time we meet, I'll use that so you see how to use that. Okay. So we have 4 possibilities. There's more than 4. There could be radiation from the fin tip. No, that's too complicated for this first class in heat transfer. So ignore that for right now. These are the 4 cases we use in our textbook. Now, you can draw a sketch here. Here's 0, here's L, here's T base. This is plotting the temperature. Here's T infinity. I'll get these in order here. Okay, I'll take up on top here, case C. This is where the temperature, given temperature at the fin tip, case C. T at X equal L equal a given temperature, T1, say. Let's take a case B. Comes down like this, and a case B, normal. Temperature profile is normal to that case B, adiabatic. Tip. Let's take a case A, convection from tip. Let's take the long fin case. Temperature of the fin approaches T infinity. Infinite fin approximation. That's typically how they look. Don't worry about what's higher and what's lower. This guy's always down here. But case A could be up on top. It's just the point being what happens at X equal L. Okay, slope is 0, adiabatic. This guy, heat's lost out of the tip. Look at my hand, dt dx. Case C, give me temperature T1 here. Heat's lost out of the end, the tip of the fin. Look at my hand, that's the slope. Case D, infinite fin. Temperature of the fin approaches the air temperature when you get out to the approach X equal L. That's what the infinite fin approximation means. Okay, so now he solves for C1 and C2 in the text. It takes a couple pages for several cases. I'm going to tell you where the results are. The results of that are in table 3-4. Table, yeah, 3-4. Yeah, that's right. Okay, just so you know again what theta over theta B is. They do a temperature difference ratio. So table 3-4, uniform cross-sectional area. Okay, case, tip condition, theta over theta B, and finally the heat lost by the fin, QF. Okay, so we take that. I'll write here, let's put case A, B, C, D here first. A, B, C, D. Okay, tip condition right here. Case C, convection from tip. Case B, adiabatic. Case C, given temperature. Case D. Case D is my infinite fin approximation. Okay, so he solved this. He's found the constants C1 and C2 for 4 different cases, A, B, C, D. I'm not going to fill the whole table in, but I'll just put a couple results down here. If the fin tip is perfectly insulated or adiabatic, the temperature distribution is this. Okay, I'll put another one down here. These are the simplest ones. The others are much more complicated. Okay. Let me say first where we know where theta over theta B came from. It came from solving this guy right here. Okay. How did they then get QF? Well, it's the same old story. In conduction heat transfer, the first thing you want to do is find out how T varies with some coordinates in time. Once you get that, then you find out how much heat transfer occurs by Fourier's law. So, Q, I'll put here, to get QF. Okay, QF equal minus Ka dt dx, where at the base x equals 0. From the picture over here, if somebody says the fin is losing heat, yeah, of course I know that. Where did that heat come from? I say, well, I think all the heat lost by the fin had to come through the base. Right, it did. And how did it come through the base? By conduction. Right, Fourier's law. So all the heat lost by the fin had to come through the base. Okay, that's what that equation says. What do you have to do? Well, you do what it says. Take d theta dx at x equals 0. Once you've got your equation here, okay, differentiate with respect to x and then set x equal to 0. That's the way he does it in the textbook. But you could also do it by QF, and that is by convection. And our convection term, let's see where our convection term is. Okay, here it is. If we look at here, heat comes out of here by conduction. It gets in the fin, and then it's taken away by the air by convection. So you can say it's leaving the fin by convection. This is the way the textbook does it. It's easier. This way is an integral over the surface area of the fin. This is the way, that's the easy way out. If you want to find QF, look at the conduction through the base. That's what he did. That's where these quantities here came from. This guy here is pretty complicated. He's got hyperbolic sines and cosines, 4 terms. 2 hyperbolic sines, 2 hyperbolic cosines, and this one. That's a big one. This one's the easy guy. By the way, capital M square root HP KAC theta B. Just remember that theta B comes outside the radical sign. Don't put it under the radical sign. It's outside. Square root HPKAC multiplied by theta B, capital M. Little m over there, square root HP divided by KAC. There's a little m and a capital M. Okay, so that's, now, if you've got, your 2995 target special calculator, it might not have hyperbolic functions in it. Okay, so here we go. The author said, I'll give them to you. Table B1, hyperbolic functions. This is in your data package for all your midterms and finals. So you have this if you don't have it on your calculator, okay? All right, so that's how we do that guy. Okay, then the next step is, all right, we're going to define something called, let me just mention one other thing. Got to be careful. This thing says table 3-4 is only good for uniform cross-sectional areas. Here's what that means. Uniform cross-section. Here's the fin coming out of the wall. This is the x direction out here. Here's x equal L, x direction. Slice the fin at a certain x direction. Slice it. What's the area? W times T. Slice it halfway down. What's the area? W times T. Slice it close to the board. What's the area? W times T. The area didn't change. It's a uniform cross-sectional area. You can use table 3-4. Here's a pin fin attached to the base. This is the base. Here's L. W measured out this way. Slice the fin out here. What's the area? Pi r squared. Slice the fin in the middle. What's the area? Pi r squared. Slice the fin down here close to the board. What's the area? Pi r squared. Okay, uniform cross-sectional area. Got it. I can use table 3-4. Oh, triangular fins. Yep, they have those guys. Here's x. Slice it at one value of x. There's how thick it is. Slice it at this value of x. Ooh, it got thicker. Slice it at this value of x. Now it's really thick. Did the thickness change? Did A sub c get bigger and bigger as I went this way? Of course it did. It's not uniform cross-sectional area. Conclusion, do not use table 3-4 for fins like that or fins like this, parabolic fins. No, won't work. Okay, just so you know when you can use table 3-4 and when you can't. Okay, so now the next step is, now what have we got so far? In that picture over there, you give me an X and I'll tell you the temperature. There it is. X equal 5 centimeters. There, L is 10 centimeters. Got it. Am I found? Got it. Okay, put it in here. Solve for what? T, the temperature at that location. Second thing, how much heat's lost by that fin? There it is for adiabatic fin tip. There it is for a very, very long fin. That's what very, very long means right there. Okay. Okay, so now we look at something called how efficient are these fins? Some fins are more efficient than other fins. So now we want to look at how we find the fin efficiency. Mm-hmm.
Does this assume there's no change in temperature with the y direction?
Right, good point. We're assuming one-dimensional heat flow. In reality, it's not. In order for heat to get out the top, there must be a temperature gradient. But the first model is assume that temperature only varies with x, not of y. We're going to do a numerical analysis problem in about 3 weeks in which it's a two-dimensional numerical problem, x and y. And you compare those results to these results to see how accurate they are. Mm-hmm. Good point. Next, we'll look at fin efficiency. Okay, fin efficiency, A to F, is defined as the Q actual, which is QF, divided by Q max. Okay, and this is the actual heat lost by the fin. Divided by the maximum heat that could be lost by the fin. So A to F equal QF over HAF theta B. Okay, there it is right there. Let's see, well, yeah, that's fine. Let's put this down. Well, did I mention that? I'll put this down. AF is the fin area. What that area is, that's the area of the fin touching the fluid. If a surface is adiabatic, no, don't include that area. Any area of the fin touching the fluid. Okay, so that means if you want to get QF using efficiency, QF is equal to HAF, efficiency of the fin, theta B. Okay. So what's this numerator, QF? There it is right there. QF is that divided by that. So what is the denominator? Okay. Look at what happens in a fin. Let's take case A, the most popular case, convection from the tip. When you're, look at this law. The bigger that is, the more heat's transferred. The bigger Ts minus T infinity, the more heat transfer. Look at close to the wall. Ooh, wow. T fin minus T infinity, really, really big. Go halfway down. Uh-oh. T fin minus T infinity, it's getting smaller, less heat transfer. Go out to the tip. Ooh, it's really gotten small now. Tf minus T infinity. This heat is going down and down and down as we go from the base out to the fin tip. What part of the fin takes the most heat out? Oh, no question, right here near the front. That's why most of the time you don't want to make a very long fin. Why waste your money? What's the payback making it long? This thing's getting smaller and smaller and smaller So most of the time, you don't make fins that long because it's just a waste of money and weight. The cost, the weight. So you say, well, what would give me a really big TS minus T fin? Well, if the fin had a temperature like this, if the fin temperature was the same as the base all along the length, T fin minus T infinity, T fin minus T infinity, T fin minus T infinity, T fin minus T infinity. Big, big, big. That's the best case. Well, you say, okay, I'll make the fin out of copper. Great. It might look like that. Or maybe I'll make the fin out of stainless steel. No, it looks like that. Copper is better than stainless steel. The temperature is more even throughout the fin length. So that's what the denominator means. Maximum heat that could be lost would be a case like this, where the fin temperature doesn't go down much at all. Okay, so now, next step. How do we present this material? Okay, figure 3, I think it's 19. Yeah, figure 319. Looks like this. Fin efficiency over here, 100% here. Let's put 100, we'll put percent. 0 down here. And then we have the x-axis, which is the one that is rather strange. L sub c to the 3/2. And then the quantity h over k ap to the 1/2. I'll mention what that is in just a minute. For the rectangular fin, it looks like this. And he defines this then in the picture. This is in the picture. He gives you all these guys. He tells you a profile. He tells you L sub c. This is all in the picture, so it's in the book's picture. Okay. Okay, so let's mention A sub P means profile area. Profile area. Okay. L sub c means the corrected fin length. To explain that, okay, here's the actual fin. Here's L. Convection from tip. This is the adiabatic tip fin. This is adiabatic fin tip. this loses heat from the fin tip. To make it adiabatic and have the same heat lost by both fins, you've got to make the fin longer. Okay. You've got to make the fin longer to account for convection from this tip where this is adiabatic. That's what's called the corrected fin length. Okay, that goes in here. That goes in here. Both these cases lose the same amount of heat. Therefore, the corrected fin length is greater than the actual fin length L. Now there's another picture here. There's three of them, but I'll just show you two of them. Here's one for a triangular fin. This is T. This is L. A profile is equal to 1/2 LT L sub C equal L. What's the profile area again? The profile area is the area you see of the fin looking at it sideways. Here's the fin. The profile area is the area I see looking sideways. I'm looking sideways. What do I see? T times L. Yep, that's it. T times L. Here's the fin over here. I'm looking at it sideways. What area do I see? Here it is, L times T. Yeah, got it. I look at a triangular fin. What do I see? Triangle. Rectangle. 1/2 length times thickness. T times L. 1/2 of that though. There it is, 1/2 T times L. Why is LC equal L? Because there's no area out there. There's no area out there. So I don't care whether it's, you can call adiabatic, you can call it convection. There's nothing there. Here, oh yeah, there's a big difference here and here. This guy here, no difference. That's why LC equal L. Now you better be really careful because now in this part, if this is what confuses people, in this part of chapter 3, you've got 3 A's. Now, just like back in chapter 3, the first part, we had 4 conditions to meet. This time there are 3 different areas. Let's take the easy one. What's A sub C, the first one? A sub C is the cross-sectional area through which heat's conducted. Okay, where my fingertip is. Where my fingertip is. Got it. What's A sub F? A sub F is the fin area, the fin area. If it helps you say, it's the fin area that touches the fluid. If the end's adiabatic, the tip is not going to touch the fluid. Don't include it in AF. AP, profile area, side view of the fin. Got it, profile area. You have to get those 3 areas straight in your mind. They're totally different, obviously. Okay, now, besides this guy, we have another one. This is figure 320. Circumferential fins. Okay, they look something like this. There's a circumferential fin, like maybe the fins on a motorcycle engine or on the cylinder. Yeah, looks like that. Okay, again, fin efficiency, 100%, 0. Same thing here, L sub C to the 3/2, quantity, H over K AP to the 1/2. Got it. There's different lines here. Each line is for a different radius ratio. R2C equal R2 plus T over 2. T is this distance. The thickness of the fin again, same thickness. R1 is this radius. R2 is this radius. L sub C, L plus T over 2. This is all on the figure. Everything's on the figure for you. A sub P, L sub C times T. Okay, so that's how you get the efficiency for circumferential fins. Now, what do you do with that efficiency? You put it right here, because you want to find QF. There it is. What's the area of that fin? Any area that touches the fluid. Air, for instance. For instance, that would be this area, the bottom area, and the side area. All three areas are A sub F. What's the profile area? Slice the fin like this. Okay, and what I see something like that. That's the profile area. What's the conduction area? That goes around the fin like that, circumferentially. Pi d times t, pi d times t. Those are the three. They're more complicated there than they are for the rectangular fin. They're more complicated to get those areas, but that's what they are. Okay, so two graphs give you the fin efficiency. You then use that in the equation to get the heat loss by the fin. Here's the fin efficiency. Or you use table 3-4 if it's a uniform cross-section area fin. Now you've got three things you can use in the library: a table and two figures. Okay, good stopping point for today. So we'll continue on with some examples then, our next class meeting, and we'll see you on Monday.